Hello, today I'm going to discuss with you one-dimensional potential barrier. So this is one-dimensional potential barrier. The height of this potential barrier is V naught. So let us consider a beam of particle mass m that are sent from the left side on a barrier. Okay. So therefore, this potential energy of this uh, barrier is V of x is equal to 0, x less than 0. V naught at between 0 to a 0 at x greater than a condition. So let us consider the following two cases um, which corresponding to the beam of energy is greater than the potential barrier and the beam of energy, I mean particle energy is less than the potential barrier. Classically, if this case E less than V naught, it is always reflected, whereas it is transmitted if E greater than V naught. However, quantum mechanically, it can be seen that there is always a finite probability for a particle to penetrate or leak through this barrier and continue its forward motion even in E less than V naught case. This phenomena is called the quantum tunnel. So this is possible because of a wave nature of the matter. So this is the first case. Here we derived E greater than V naught case. By using Schrodinger equation, we can get the solution, right? Okay, this is get the solution. So this is desirable the solution of uh, particular in this case E greater than V naught case. Next, very important case is the E less than V naught case. Here the three regions are there. Region 1, region 2, region 3 are there, right? So boundary condition x is equal to 0 and x is equal to a. X is equal to 0 and x equal to, right? So therefore here, uh, so generally the classically we expect a total refraction in this case E less than V naught case. Every particle that arrive at the barrier x is equal to 0 will be reflected back. So no particle can penetrate the barrier when it could have a negative kinetic energy. So now we're going to show that the quantum mechanical predictions different sharply from their classical counterparts from the wave function is not zero beyond the barrier. So for that, here I'm going to, there is already here I derived solution of these three regions. So this is the first region, v equal to 0, first region, right? V equal to 0. So try to substitute Schrodinger. This is Schrodinger equation, right? E square psi divided by dx square plus Vm divided by h cross square E minus V of psi equal to 0. So in case if you try to substitute V equal to 0 here, then you can get this equation. Specifically, I mentioned here the number 1. Okay. So this wave function represented the wave function at region 1. So therefore, the solution of this equation is like this. Here I am using in place of 2m divided by h cross square is equal to k square. The solution of this equation is, so whereas come to second region, so v equal to v naught, right, in between 0 to a. So here I try to substitute v equal to v naught, then I can get the solution. The region 3, v equal to 0, I mean potential energy 0 in region 3. which means the x greater than a region is all region. So if you try to substitute the Schrodinger equation, then you can get this. Here I got a very interesting solution. If you try to observe here, this is d e power I kx plus d prime e power minus I kx. So here I'm going to come this first solution. Here wave function 1, this is wave function 2, this is mean this is Schrodinger equation solution at region 1, region 2 solution, region 3 solution. In case if you try to observe here, okay, here again I'm going to explain here, no need to worry about this thing. So in region 1, in case if I incident one energy is, okay, this is the e power I kx. So instant energy amplitude here I'm considering 1 complete. Then I can get here the after incident some reflection is happening at the boundary condition x is equal to 0. So this is the that function a e power minus I kx is reflection. After that it will transmitted here. It will enter in pattern. It will enter the region 2. Here we can get the d e power alpha x exponential increasing and exponential decreasing. Whereas come to the third region, here there is no reflection. So which is why I'm going to consider this portion is 0. Then I can get this is the final solution. Okay, this is equation number 3. This is equation number 3. Very important. So by using these three solutions, in case if you observe clearly, so we got the different type of constant values a, b, c, d, right? A, B, C, D value constant. So here we are going to find this A, B, C, D constant. No need to find all the coefficients here. So particularly I want here the probability density of incident and reflection and transmittance are equal to 1, right? So we already know this one. The incident reflection transmit equal to 1. Therefore, I need to know this A value and B value. So because this is a instant wave probability, this is a transmission by the probability. So the probability density for incident and transmission coefficients, the reflection coefficients, this is the reflection coefficient, right? This is the transmission coefficients. We need to find this reflection coefficient, transmission coefficient. For that we need to derive what is the A value here, what is the D value by using this solution. For that we have the two boundary conditions. So first boundary condition, if you in case if you apply the first boundary condition, region 1 region 2 solutions are equal, then you can apply the second boundary condition here. If you apply the first boundary condition, then you can get this one. Then you can try to differentiate these things, then you can get this one. So again, if you try to apply the second boundary condition, this is a solution, right? This is barrier. Okay, so this is barrier, right? This is region 3, this is region 2. At x is equal to a point, the wave function is continuous, which is why I'm going to use here wave function 2 equal to wave function 3. Okay, these are the two equations. Then in case if you try to differentiate this equation number 6, d by dx equals number 3 and d by dx, then we can get this. So then you can multiply equation number 6 into ik. This one is subtraction, equation number 7. Then you can get this. This is all the derivations. No need to worry about the derivation. Just go here, read all these step by step derivation. So no need to worry about this derivation. You can get easily. So in case if you try to solve this, then finally you can get A and B values here. So this is how I derived this step by step. Then find and see A value, then B value. So finally I can got A value, B value, C value. Then finally I substitute all the coefficient in the equation number one. I mean equation number first. So then I got the final equation D equal to first. This is the final equation I got. D equal to minus 2ik alpha e power ik divided by this thing. So here is important this transmission coefficient value D can express the in terms of probability, right? D modulus square. Yes. So we know the I star psi. So like that, this is D value. In case if we try to complex conjugate of this equation, then we can get here the minus. Wherever I is there, that sign is going to change, right? Remaining all things are same. Then I try to multiply D and the D complex value. Here, this is only D. You need to find D complex at least. Find D complex from this equation, then you can get D complex here. Then multiply D complex value and the D value. This is D value. Then you just try to apply the complex. For example, I is there here. I'm going to apply complex. What will get here? Minus I, right? Like that you can apply here. Then you can get D complex value in the type of equation. Then you try to multiply these two equations. Then you can get 4 a square alpha square divided by alpha square minus c square. So we know R plus reflection plus transmission equal to 1, right? So from that equation, reflection is equal to 1 by t. We already got the t, right? Then we can get R value, reflection value. Okay. So this is very, very important, the reflection value, transmission values. So here is a very, for example, broad high barrier is there. In that case, alpha A greater than 1. So therefore, this sin hx term is going to tends to be 1 divided by 2 e power alpha or cos h x term. I mean, in place of x, alpha A is there. So in case if we try to substitute this in place of sin h alpha A term 1 divided by 2, then you can get the value. So this is the 15 equation. Number 15 is the final equation. So we know the k value, k equal to k square is equal to m divided by h cross square, right? So from derivation we know this is k square equal to 2m e divided by h cross square, and alpha square equal to 2m divided by h cross square v naught minus c. If we try to substitute k square alpha square value here, then you can get this equation. So in case if you simplify, finally you can generate this equation. So this is all simple derivations. No need to worry about this. This is the transmission value, final equation. Very, very important. Here this term is there. Exponential minus E alpha A. Very, very important. This is the distribution of wave function in region 1, 2, 3. The reflection coefficient or transmission coefficient. So this equation represented the transmission coefficient. In case if you try to find the probability of a transmission and E divided by V naught in terms of potential, then you can get this type of graph. Exponentially decreasing factor. Here minus e power minus 2 alpha A is there. This is the solution and um, how to get this transmission probability, I mean transmission coefficient, the reflection coefficient of this function. Okay. So here in this portion, the dashed portion, this figure gives the transmission probability, whereas the particles are the less than the height of the barrier. The transmittivity decrease monotomatically as E decrease below V naught. This is reflection to as a tunneling through the barrier. Okay. So what are the applications of this one-dimensional potential barrier? So number one is the field emission of electrons from the cold metallic surface. Very, very important this one. And second one is electrical breakdown of insulators, tunneling effect. Third one is the reverse breakdown of semiconductor diodes. And the fourth example is application of this one-dimensional potential barrier, switching actions of the tunnel diode. We all know this example, the application of a tunneling phenomena, emission of alpha particles from the radioactivity. These are all uh, the tunneling effect um, provide the explanation for the this phenomenon. Okay. So this is very, very important. So these are all we already know. The emission of alpha particles, radiations already, field emission of electrons from the colloidal, electrical breakdown, we know, reverse saturation, uh, switching actions of a tunnel. So these are all the tunneling effect provides the explanation for the this phenomena. In case if you want to know these things, then I can write here. First thing is the first field, the field emission of electron from cold metallic surface. One explanation, and second explanation is the emission of alpha particles from a radioactivity element. So this is all about the one-dimensional potential barrier. So I can explain in online also on step by step, but it will take almost 2 hours, 1.5 hours. So that is not good for watching this type of videos. So for that, I already derived this thing, then I can explain. Okay. So I hope you can understand this because of all this derivation, right? So in case uh, you got any doubt from the derivation part, just please try to comment below, then I can reply. Okay. This is all about the one-dimensional potential barrier. It's a very simple thing, right? So just derivation, but you need to understand here after getting this solution. So this portion is very, very equation number 1, 2, 3 there, right? This portion is very, very important. So in case if you try to observe here, solving equation number, solving the equation in a region 1, in region 1 potential energy is 0. Then you got the solution, this type of wave function psi is equal to e power I kx. So I kx is there, I kx. plus some amplitude is there, some amplitude here. Here I didn't use any amplitude. Here I use only amplitude of this incident wave is 1. The reflected wave amplitude is A. And again this wave is entering into the third region, is second region here. In that case, one exponentially increasing function is there, exponentially decreasing function is there. This is the exponentially increasing function. This is the exponentially decreasing function. After that, it will enter into the transmit into the third region. Then it will decrease going on like this, right? That is the e power d. This is coefficient, the transmission coefficient d e power I kx. In region 2, there is no reflection, which is why I'm going to neglect this. So these are the key points. In case if you understand this thing, then you can get it. So remaining all these things are, you need to find the reflection and this transmission coefficients. These are all derivations. No need to worry about this derivation. If you want this, yes, if you want PDF of this file, try to comment below, then I can send this PDF to. Okay, it's all about the derivations. You can go step by step this derivation. Finally, you can get the d value and t values. So then you can get the final answer, transmission probability over all the value. Okay, these are the uh, examples of the tunneling. This is all about the dimensional potential barrier.